Hello students, let's begin Module 12 for Week 12. As you can see, there are so many sections here, but don't worry. This notebook is Module 12 and 13 put together because I still don't have good idea where to cut it. Maybe we can cover up to section 3, maybe up to 4, I'm not so sure. So I have just one big notebook here. We'll cover as much as possible in week 12 and then the rest will be covered in module 13. Okay, let's begin. Determinant of order 2. Determinant is a function from a n by n square matrix into the set of real numbers. And the computational formula for 2 by 2 matrix is very simple. AD minus BC. This diagram will help you. Multiply the principal diagonal, multiply the other diagonal, and principal has positive direction, the other has negative direction. So AD minus BC. Okay, I don't think it's necessary to do an example here, so let's just move on. A good application, a very important application of a determinant is the inverse matrix. So inverse formula for 2 by 2 matrix goes like this, 1 over AD minus BC, and then this matrix here. Switch the principal diagonal and then negatives. How do you prove it? Well, just by brute force computation. This part is the candidate of the inverse matrix, and then we just do the matrix multiplication. First row times first column, first row times second column, second row times first column, second row times the second column. You get this, 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 and that, and simplify. This and that will become 0, and these two will turn out to be AD minus BC. So upon dividing by that, yes indeed, I get the identity matrix. So if you encounter any 2 by 2 matrix, you can easily calculate the inverse matrix using this formula. If you have 3 by 3 or higher, then you'll have to go through the Gaussian elimination or whatnot. But for 2 by 2, it's easy. Here's some properties of determinant. The determinant is bilinear. That is, if you fix one column, with respect to the other column, we can separate the addition and we can separate out the scalar multiplication. So fix the red column, and then if you have linear combination to the first column, we can separate out like this. And also the same, fix the first column, and second column has linear combination, we can separate out like this. It's bilinear. Two linearities put together. Next property, alternating. So if we switch two columns, then negative sign. Some people call it anti-symmetry, but the term I'd like to cover is alternating. By the way, as an immediate consequence, determinant of x comma x, if two columns are the same, then you have to have 0. It's clear, right? X comma x, switch x comma x. So what do you get? We get the same determinant except for negative sign. What kind of number is equal to the negative of itself? Only 0. Finally, determinant of an identity matrix is always 1. I don't know the name, identity property or unity property, I don't know. I don't remember. Maybe both of them are right. So those are standard properties of determinants. And then there are some further properties. Determinant of a transpose is the same. Determinant of product of determinant. And finally, determinant of inverse is 1 over the determinant. Let's see, can we easily check the determinant of transpose? If I take transpose, instead of BC if I just transport and CB, and then apply the same computation, multiply the principal diagonal AD, and subtract this, well, same, minus BC. So yes, determinant of transpose is the same as determinant of the original. How about the multiplication? That's a bit tricky, but I can prove it by brute force computation. And well, it's a bit ugly, but here we go. Determinant of ABCD, determinant of UVXY, it's AD minus BC times UY minus VX, and if you calculate out, this is what we get. Now let's calculate the matrix multiplication first. ABCD times UVXY, and then we end up with this 2 by 2 matrix, and then take the determinant, multiply the principal diagonal, and then subtract the other product. Now, is this determinant the same as the determinant of product, which ended up like this? Well, it requires some really tedious computation, as you can see, but they end up the same. So they are the same. How about the determinant of the inverse? Well, if I write an exam problem, this is the only possible one, because I cannot write a problem like this in an exam. It's too tedious. And this one, come on, too trivial. This one, it's left to the students. Okay, all right. But I don't know if it is just right or too, maybe a bit too easy. But okay, I'll leave that to students. It turns out that A times A's inverse is identity, and the determinant of the identity is 1. Okay, that's where I'm going to stop. I think I gave you a bit already too much hints already. Finally, this property. Let a map phi be a real function with two 2D vector variables with the following properties: bilinear, alternating, and identity property. Bilinear, what do you mean by that? I can separate out the linear combination to the first vector and do the same thing to the second vector. Oh, wait a minute. I missed a color here. Okay, all right. Okay. So bilinear, just like the determinant is. See, determinant function has bilinearity. So a certain map has bilinearity and also alternating property. Yeah? X comma y minus y comma x, all right? And then one more. Phi of identity is 1. And this is 1, 0, and this is 0, 1. Okay. Then this map phi is determinant. That's a striking property because we define the determinant using this formula here, AD minus BC. At least for 2 by 2 matrix, this was the definition. And these three properties were just properties of determinant that we could prove using some brute force computation. But what this thing is saying is, if you have a real function with these properties, these three properties, it must be determinant and nothing else. So it's really striking. And this theorem, this is going to be very, very important if we move over to higher dimension. Because for higher dimension, the computational formula is not going to be this simple. So it's very, very difficult to define determinant. And even if we have an expression, does it make sense? Is it well defined? Is it unique? We just end up with a can of worms. But if we establish this, then determinant is well defined and unique. That part is all set. Computational formula, there may be 15 different types of computational formula, but they will all mean the same thing because we have uniquely defined determinants. So this is theoretically very, very important. For 2x2 case, it's really simple. Okay. All right, let's prove. So if you have first column AC, second column BD, like this, AC, BD, and using those properties by linear alternating in identity property, we have to prove that this is AD minus BC. In the end, am I getting AD minus BC? Yes. Let's follow this from here. We can separate this AC using A0 plus 0C and this BD by B0 plus 0D. That was easy. Next, we can multiply, we can bring this A out, C out, B out, D out, so that we have 1, 0, 0, 1, 1, 0, 0, 1. So what did we end up with? We ended up with a linear combination AE1 plus CE2, BE1 plus DE2, where E1 is 1, 0, this is 1, 0, E2 is 0, 1. Blue from the first vector, red from the second vector, but E1, E2, those are the same. All right. Now we have all those formal expressions. Let us use the properties by linearity, and we can separate the first vector here, and then by linearity again, separate out the second vectors. So we have E1, 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 E2, E2, E1, E2, E2, and then we have appropriate coefficients. Can you follow all the computation here? A phi and C phi, and with this we have BE1 DE2, so BE1 DE2, and here C is there before, and BE1 DE2, so BE1 DE2. So we get that. All right, let's do a bit of a computation here. E1, E2 there is equivalent to, let's see, no, not this one, this one. E2, E1, change it to E1, E2, and we have negative sign using the alternating property. So this plus becoming minus because I switched these two, alternating. And then E1, E1, E2, E2, those are zeros. If we switch the order, we have to have negative of that, but I got the same thing even after switching. So what number is the same as negative of itself? Only 0. So that's 0, and that's 0. So what do we have? Only middle part. So AD minus 1, this is 1, 0, 0, 1. This is identity matrix. And BC minus 1, and why am I having this residual parenthesis here? And crossing out these zeros out, only one part will survive. We indeed get AD minus BC. This kind of proof, I think everybody should be able to reproduce about this level out of scratch. It's just proof by algebra, starting from the left-hand side, and then just working out, and then you're going to the right-hand side using appropriate properties. First several steps may have been a bit tricky, decomposing, addition, and then getting those linear combination. But once you get up to here, that's straightforward. We are using bilinearity, and then alternating, and then for identity 0, identity 1, and then alternating 0. So we proved the uniqueness. The proof was kind of like that, but the implication is significant, by the way. The uniquely defined, well-defined determinant. And by the way, the proof method and all these kind of things will just carry over to higher level as well. So this theorem will stay valid for higher order n by n matrix, like 100 by 100 matrix. It'll still hold. The computational formula, that applies for 2 by 2 and no more. Alright, so much for 2 by 2 matrices, and then a determinant of some 2 by 2 determinants. Determinant of some, I don't know, -2, 6, 3, 3. This kind of computation. I don't think this kind of thing will cause any kind of trouble to anybody, so I'll just leave that to students. And this kind of problem, I used to write this kind of problem in pre-calculus class. This is linear algebra, so just set it up and solve the equation, and that's going to be it. So I don't think this is going to be a problem. So let's just move on. We'll say we are done with order 2, and let's go to order 3. And before going over to order 3, let's consider determinant of order 1. Our textbook author does not discuss this because he must think this is just trivial. Okay, 1 by 1 matrix is just a real number, so all the arithmetic rules apply. Just real number arithmetic rule. No problem there, right? So determinant of 1 by 1 matrix is just itself, and consequently it's linear. It's itself, though. And then preserves the multiplication, because itself is multiplication. And then invertibility. Yeah, I mean, inverse matrix, the inverse is 1 over a, and if the denominator is 0, we can have that. As long as denominator is non-zero, yes, we can. So it works out as well. Determinants determines invertibility. Okay. And then determinant function is unique. Oh, that's too trivial. Never mind about determinants of order 1. It's just the same, just a real number itself. So no problem there. Now let's consider determinant of order 3 in separate video. Let's stop here. We completed determinant of order 2 and then the determinant of order 1.